Hey Kim team, I hope you're all doing well on this Thursday morning here. A little bit of an update for you as we are getting going here at the start of the video. We are going to be sending out, all teachers are going to be sending out either an email, a text, calls to you and parents, and we're needing responses back just to make sure that you are keeping updated on emails, that you're staying in contact with teachers, that you're doing okay. Everyone's going to be sending that out to their second period classes. So my second period, be watching out for, I'm going to send out an email for the first round, and if I don't get a response from the email, then I'm probably going to be calling you and your family. So please, 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 you have to respond to the email, because if you don't, I'm just going to be trying other ways, and then I will eventually catch up with you. But please respond to that, to all of your teachers, so that we know what's going on. We're going to pick up here with our Unit 4 stuff. So just wanted to get started with a little bit of review, kind of get back into our natural methods that we do in the classroom, starting with our do now. In 3.9, we had talked about ionization. So just think for a second, the charge on a completely ionized magnesium atom, what would that be? If we take a look at the periodic table that I have here, we see magnesium is 12, and the nearest noble gas is 2 spots behind it, right? Magnesium 12, neon is 10. What if we go the other way? 1, 2, 3, 4, 5, 6 spaces is argon. So we can either gain 6 electrons or lose 2. Losing 2 requires less energy, so magnesium is going to be 2 plus. What about if we go phosphorus, ionized phosphorus? Well, if this was being transferred over to an ion, phosphorus, we have 1, 2, 3, or 1, 2, 3, 4, 5. So gaining 3 electrons here is less energy, so it's easier for the phosphorus, which means P3 negative, right? Gaining 3 additional negative charges, and turning that into a P3 minus ion. Last thing, writing out the electron configuration for a lead 2 plus ion. I'll give you a second here. You can pause the video if you want. All right, the lead 2 plus, lead is normally 82, right? And if we do subtracting 2 electrons from the electron configuration, it should be lead with an electron configuration that resembles mercury. So this would be in the 6th row here, D block 5D, sorry, this keeps pulling up different atoms, 5D10. Mercury is the end of D block here. So you should write out the electron configuration to end in 5D10. I'm going to move on today. It's something that I really miss not being able to do in the classroom, because I think it's probably the single most important chem concept that we're going to go over as an individual standard. It's called Coulombic Attraction. And what this is it's the attraction between charged particles. And it is what's responsible for almost every single atomic interaction that we have. If we were doing this in the classroom, and you may have heard some students refer to this that had my class last semester as Magnet Day, I would give you some magnets and I'd give you some time to complete this objective here. So there are two factors that affect magnetic attraction, and I would just allow you and your group, given the magnets, to do a little bit of research in the lab stations, figure out how do you change the amount of force that is attracting the magnets? How do you make them more attracted versus how do you make them less attracted? There's only two things that affect the attraction between those magnets, and it works the same for charged particles. If you have magnets at home, I would pause the video now and I would try this experiment out. After you do this, or if you're just watching the video, we figure out that the two factors are distance and amount of charge. So think about with magnets, okay? If you hold them very, very close together, they're going to be attracted super strongly, right? Versus if I held them like a football field away, they wouldn't really have any attraction. The greater the distance, and actually, you know what? I am going to come over here and I'm going to draw this out because I think that would be helpful. Okay. With magnets, right? The greater the distance, and I'm putting some arrows to try and show attraction. The greater the distance, there's not as much attraction here. Okay. So these two magnets, or these two charges, should be way more attracted than these two charges. The other factor that affects Coulombic attraction is number of charges. So if you had a very strong magnet, right, that has more charge capability in it, then it will be more attracted to something. When we're talking charged particles, right, we are talking about electrons, protons. So if we have something that's like 4 positive charges, 4 negative charges, that is going to be much more attracted between those two entities than, say, something that is just 1 proton, 1 electron. That's not going to have a ton of attraction here. So I'm going to draw smaller arrows. So this is much more attractive because it has more charges. There's just more particles that can participate, more charges that can participate in the attractive forces. All right, I'm going to exit out of this, and I'm going to go back. No, I don't want to save. Sorry, I misclicked. Let's go back to our presentation here. Okay, come on. Okay, so here, oh, no. Why is there so much lag on this? Okay. Let's say we go down to the actual particle level to check. Relative attraction between 3 different sets. Okay, so I'm separating these top pair, the middle pair, and the bottom pair are all different things. Oh, there's a pointer. Okay, so these we're considering separate from these, which are separate from these in this problem. which pair should be the most attracted and why? If you were saying the bottom pair here, that's correct. They're all the same distance, right? So the factor of distance doesn't apply, but we do have different number of charges. So 3 plus 3 minus, that's 6 total charges. Compared to 2 plus 2 minus, that's 4 total charges. 1 plus 1 minus, that's 2 total charges. The 6 total charges are going to be more attracted to each other. If we keep moving forward, we again have 3 different pairs: the top pair, middle pair, bottom pair. Which one of these pairs should be most attracted and why? If you said the top pair, that's correct. Again, we're looking at our 2 factors, distance and number of charge. Each of these has the same number of charges, right? 1 plus, 1 minus, 2 charges overall. So the charges aren't changing. Distance, though, is changing. Looks like we have close, medium distance, far apart. So the closer ones are going to be more attracted than being far apart. So this pair is more attracted to each other. There's less distance that the charges have to reach across. Make sure that you're not getting this confused with the potential energy that we talked about earlier. These charges would have more potential energy, right? Because they are pulled further apart. They're pulled in the opposite directions of their attraction. But that is not their actual attraction. When we're talking their actual attraction, these have greater attraction. These have greater potential energy because they could fall further into each other. Those are not the same thing. So make sure that you know that these are more attractive. Okay, this is where we're going to start cutting out some material. There's a lot of chemistry that we need to get through that I feel like is really important in just looking at Unit 4. This concept is really important of Coulombic attraction, but the other the next 4 standards aren't very important, so I'm going to kind of skip around after this. The video's not probably going to feel very satisfying because there's not really going to be a conclusion beyond what we've already talked about. I just want you to think for a second. These 2 examples, is that as simple or as complex as a real atom? And what's different about the way that this atom is arranged compared to like how these charges are arranged? I'm going to skip over to my slides here so I can draw. Okay, let's see. What's a good color here? Let's say you were really concerned with this electron here. This blue one, number 8. In order for this electron sorry, that is not the right question. This electron, because it is negative, it is going to be attracted to the positive nucleus. However, there are things in the way, right? These 2 electrons on the inside repel this electron, and these electrons in the same ring also kind of repel this electron a little bit. So we're going to skip over it, like I said, but the next slide, if you want to look at it, and it might be helpful for those of you going AP next year, talks about effective nuclear charge, which is essentially how much charge does an electron feel from the nucleus? How attracted is that electron? So an electron out here, right, like this, is going to feel pull from the nucleus much less than an electron here in the middle. I'll give you a second to think about why that is. First of all, distance, right? Our two factors for Coulombic attraction are distance and number of charge. This electron in this far out ring is so much further away that it's already going to be feeling less charge than an electron close up. The second thing is that you have all of these electrons that are also negative charges that are going to be repelling this outside electron. So the outer electrons aren't as attracted to the nucleus as the inner electrons. And the inner electrons feel a ton of attraction towards the nucleus. This is what allows that ionization to occur, because the outer shell electrons aren't as attracted to the nucleus, so it's easier to lose them and ionize them. I'm going to keep moving forward here. My computer is going to need a sec because for some reason the drawing tool takes a lot of the CPU. Okay, I think we're almost done here. So this is what I was talking about, effective nuclear charge. So you pick an electron to think about. The electrons in between that electron and the nucleus cancel some of the nuclear charge, and the electrons outside have no effect on this electron because they're not in the way of the charge. So you can calculate this with something called Z effective, or the effective nuclear charge is equal to Z minus S, the number of protons minus the shielding constant. Starting with this slide, if you are not interested in effective nuclear charge, you do not have to continue watching this video. I'm not going to cover this. It's not something I expect you to know, because it would require us going a lot more in depth, and there's better things we can do with our time. So there's Slater's rules here. You can look at these. They tell you how to calculate the value of S. So this is Z minus S. Z is always going to be the atomic number, right? The number of protons. S changes depending on which electron you're looking at. So you can use these three rules here to calculate what that value of S would be. I go through this a little bit more. If you want to calculate the effective nuclear charge for a 1s electron or a 2p electron, we're not going to deal with calculating attraction either. It's just not something we need to spend our time with. I do want to talk 4.2 all the way through 4.5. I'm going to cut. They're all trends that deal with Coulombic attraction. As long as you understand Coulombic attraction and you know that the two factors that affect Coulombic attraction are amount of charge and distance, we'll be fine. You don't need to know atomic radii, ionic radii, ionization energy, or electronegativity. We'll come back. My next video will be on 4.6 and 4.7, and then we're going to jump to Unit 5. So again, if you're going to take AP, you can look at 4.2 through 4.5. They might be helpful. We might also come back again and talk about them in AP, but it's not something that I'm going to require you to know. that's it for the video then. I hope that you're finding these helpful. A lot of people have said that they are. Remember to check in with your teacher. Okay, second period, I'll be sending out those emails later today. And hope that you are all doing well. Bye, everyone.